Good morning, students. Today we are going to discuss about a new chapter, mechanical properties of fluids. We know matter can be divided broadly into three types. One is solids, another one is liquids, sorry, another one is liquids, and third type is gases. Here, solids cannot flow from one place to another place, whereas liquid can flow from one place to another place, and gases can flow from one place to another place. So here, liquids and gases can flow, can flow, and are therefore we call them as fluids. Fluids are nothing but the materials which have flow property are called fluids. Fluids are nothing but both liquids and gases together called as the fluids. Next, see here, fluids have no definite shape. That means fluids means liquids and gases do not have no definite shape of their own. That means liquids and gases occupy the shape of the container. Therefore, they occupy the shape of the container. This is one point about liquids and gases. Together we call them as fluids. And another one is nothing but solids and liquids. Second point is solids and liquids have definite volume. They have definite volume, whereas gases have no definite volume, whereas gases fill entire volume of the container. That means volume of the solids and liquids is fixed, and whereas the gases, if we fill the gas in a room, that gas will be occupied in the total volume of the room. That means gases fill entire volume of the container. They do not have fixed volume. Okay, and solids and liquids have, another point is solids and liquids have much lower compressibility. As compared to gases. That means as we know, we have discussed already in previous chapter, solids and liquids have greater bulk modulus, so that they have lesser compressibility. As compressibility is less, the volume remains constant. If the volume remains constant, density of the solids and liquids almost remains constant. But gases do compress easily. We can compress the gases easily, so that the volume of the gases changes, so density of the gases also changes. Okay, this is all about general idea of solids, liquids and gases. Now I am going to discuss about pressure. Pressure is nothing but, see here, when you take an object, I am taking a container like this, and consider this container is being filled with the liquid, that means fluid. This container is occupied by fluid. I am inserting an object, submerging the object inside the fluid. This is all nothing but fluid, an object. This is an object, and see here, when the object is kept inside the fluid exerts normal force like this. Fluid exert normal force like this. Okay, this normal force or perpendicular force per unit area is called as the pressure. Okay, normal component of force or perpendicular component of force, exerted by fluid on the object per unit area is called pressure. We call it as hydrostatic pressure. So pressure can be defined as pressure equal to perpendicular component of force exerted by fluid on the object per unit area is called pressure. So here, if the cross-sectional area is less, the pressure will be more. That means here pressure is inversely proportional to cross-sectional area. If area is less, pressure will be more. They are inversely proportional. Pressure will be more. See, when an elephant step onto your chest, that is the area occupied by the foot of the elephant is less, so pressure will be more, so that our ribs will be cracked. When elephant directly step onto our chest. Next one, when an elephant in a circus, we see that in a circus the performer keeps strong and wider plank means wooden object on his chest. So area increases when elephant step onto the plank. When an elephant step onto the plank, the performer in the circus feels less pressure. Why he feels less pressure? Because the area of the plank is more. As area is more, pressure will be less. Now, the pressure is nothing but force per unit area, perpendicular component of force per unit area. The units are, for force the units are newtons, for area the units are meters square. So the SI system of units for pressure are Newton per meter square, which is being named as Pascal on the name of the scientist Pascal, Blaise Pascal. Okay, so Newton per meter square equivalent to Pascals. So SI units of pressure are either Newton per meter square or Pascals. Okay, and the common unit common unit of pressure is atmospheres. So atmosphere is nothing but pressure of the atmosphere at sea level is called atmospheric pressure. Pressure of the atmosphere at sea level is called atmospheric pressure. Is called atmospheric pressure. Here 1 atmosphere is equal to, in SI system, 1 atmosphere is equal to 1.013 into 10 to the power of 5 Pascals. Pascals are the units of pressure in SI system. Okay, this is all about atmosphere. See here, we define that pressure is the perpendicular component of force per unit area. It is just component of force, not the original force. So here pressure is a scalar quantity. Pressure is a scalar quantity. Force is a vector, but here we are not taking force, entire force. This is nothing but perpendicular component of force, normal component of force. One component. That one component will be lie along only any one of the direction. So pressure is a scalar quantity here, not a vector quantity. See, here we are going to define one more term, that is density. Density. Okay. Density is nothing but mass of the substance. Mass of the substance per unit area. Mass of the substance per unit area is called density. Sorry, mass of the substance per unit volume. Mass of the substance per unit volume is called density of the object. So here density is nothing but mass per unit volume. Okay, the SI system of units are SI units for density or kg per meter cube. Kg per meter cube. And CGS system of density. CGS units are nothing but gram per centimeter cube. Gram per centimeter cube. Gram per centimeter cube is also can be written as gram per cc. Cc stands for, cc is nothing but cubic centimeters. Cubic centimeters. Cc is nothing but cubic centimeters. We can see 1 kg per meter cube is equal to how many gram per cc, or how many grams per centimeter cube. So here 1 kilogram is nothing but 10 power 3 grams, 1000 grams, divided by 1 meter is nothing but 100 centimeters whole cube. That is nothing but 10 power 3 grams divided by 10 power 2 whole cube is nothing but 10 power 6 into centimeter cube. That is nothing but see here 1 kg per meter cube is equal to 10 power minus 3 gram per centimeter cube, or cubic centimeters. Okay. So 1 kg per meter cube is nothing but 10 power minus 3 gram per centimeter cube, or gram per cc. Gram per cc. Okay. Now this density is also a scalar quantity. Density is also a scalar quantity. So here the final conclusion is liquids and solids are almost incompressible. Incompressible means they do not compress. Incompressible. So volume remains constant. Volume remains constant. Therefore, density nearly constant at all pressures. At all pressures. Okay. Now we are going to define relative density here. Relative density is nothing but relative density is equal to density of the substance divided by density of water at 4 degrees Celsius is called relative density. The units of relative density are no units because it is the ratio of same two physical quantities. It is a dimensionless physical quantity. Relative density is a dimensionless physical quantity because it is the ratio of same two physical quantities. Now we are going to discuss about variation of pressure, variation of pressure with depth. Variation of pressure with depth. Students, here I am taking a container. I am taking a container like this. This container is being filled with a fluid. Like this. Like this. I am taking some part of this fluid. This fluid is at rest. I am taking this part of the fluid. Okay, consider this is 0.1 and this is 0.2. Okay, see here the pressure exerted by, force exerted by fluid at rest on the object is given by force is equal to pressure into area. Here this force is here the force exerted at first point is nothing but this one. Let us consider the pressure exerted at point 1 is P1. Let the pressure exerted at point 2 is nothing but P2. Consider this as P2. Okay. So see here, point 2 is at a depth of h below the point 1. And we know that the force exerted by fluid from all sides in perpendicular manner and like this. This is the force exerted by fluids in all sides like this. And we know the base area, let the base area of the imaginary fluid cylinder, base area of the fluid, this area is A, fluid, that we have considered it as imaginary cylinder. Its base area is A, and height of the cylinder is nothing but h. Height of the cylinder is h. This height is nothing but h. from here to here, the height is h, and base area is A, so that now the volume is given by volume of the imaginary cylinder. Volume of the imaginary cylinder is nothing but volume V is equal to area into height is nothing but volume. So now how many forces are acting on the object? One is force due to, three forces are acting. One is force due to pressure at top level at point 1, which is pointing downwards. It is a downward force. And second one is nothing but force due to pressure at point 2. This force is pointing upwards. And third one is nothing but weight of the imaginary cylinder. This one. Third one is nothing but weight of the imaginary cylinder. This force is pointing downwards. And the fluid is at rest. We know that the fluid is at rest. So as the fluid is at rest, as fluid is not flowing, as fluid is at rest, sum of forces must be is equal to 0. That means sigma fx equal to 0 and sigma fy equal to 0. There are no x component of forces in this picture, and there are only y component of forces, and those y component of forces are, one is force due to pressure at top and force due to pressure at bottom, and another one is nothing but weight of the imaginary cylinder. So I am drawing free body diagram here. The free body diagram is nothing but the force due to pressure at point 1 is downwards. This force is nothing but pressure P1 into area. We defined that force is equal to pressure into area. Okay. Second one is nothing but force due to pressure at point 2. At point 2 is upward force. So this force is equal to P2A, upward force. And one more force is nothing but weight of the imaginary cylinder. Weight is nothing but mg. Okay, three forces are pointing here, F2, F1 and mg. So as sigma Fi is equal to 0, here sigma Fi is nothing but one force P2A is pointing upwards, plus summation is nothing but plus, and mg is pointing downwards, so I am writing it as minus mg. Summation is there, so I am keeping plus, and minus P1A is pointing downwards is equal to 0. Therefore, P2A minus P1A, I am taking A as common, so P2 minus P1 into A equal to m into G. We know that density is equal to mass by volume, so mass equal to density into volume. Therefore, I am writing P2 minus P1 into A is equal to mass can be replaced with density into volume into G. And we know that volume is equal to area into height. So P2 minus P1 into A is equal to density into volume is nothing but area into H into G. Here area and base area cancels together. So now P2 minus P1 is equal to rho G H. That means here pressure difference depends on density of the fluid, depth h, and acceleration due to gravity g. Acceleration due to gravity. Pressure difference depends on density of the fluid, depth, and acceleration due to gravity. See here, when this point 1, when point 1 is shifted to top of the fluid, when point 1 is shifted to sorry, when point 1 is shifted to top of the fluid, that is open to atmosphere. So at point 1 the pressure is nothing but P1. So P1 is equal to simply at P atmosphere, that is nothing but PA. When this point 1 is shifted to top of the fluid, this pressure at point 1 is nothing but P1 is equal to P atmosphere. It will become atmospheric pressure. So P1 equal to P atmosphere, and let P2 is equal to simply P. Therefore, the pressure difference P2 minus P1 equal to, we know that, rho GH. So now P2 is being replaced with P minus P1 is nothing but what? Atmospheric pressure is equal to rho GH. So here P minus PA is nothing but excess pressure, a difference of pressure. The excess pressure P minus PA is nothing but pressure difference or excess pressure at depth H. Is called, this excess pressure is called the gauge pressure, at that point. Okay, now P minus PA is equal to rho GH. Therefore, P is equal to PA plus rho GH. So here this P is called absolute pressure. So absolute pressure is equal to atmospheric pressure plus rho GH. Therefore, absolute pressure is greater than by atmospheric pressure by an amount of rho GH. Absolute pressure is greater than atmospheric pressure by an amount of rho GH. Now here absolute pressure is equal to atmospheric pressure plus rho GH. We know that atmospheric pressure is equal to 1.013 into 10 to the power of 5 Pascals. Right. Here I am going to define Pascal's law. Here Pascal's law is nothing but the pressure in a fluid at rest. The pressure in a fluid at rest is the same. Pressure is the same when the fluid is at rest at all points if they are if they are at the same level. So to justify this point, I am taking a container. I am taking a container like this, and this container is being filled with fluid. Let pressure at this point is nothing but PA, and pressure at this point is nothing but PB, and pressure at this point is nothing but PC, and pressure at this point is nothing but PD. Okay, this point A, point B, point C, point D are at the same depth from top surface. And this top surface is open to atmospheric pressure. Therefore, absolute pressure at point A is given by PA is equal to atmospheric pressure plus rho GH, and absolute pressure at point B is given by atmospheric pressure plus rho GH again. Why I am writing H? Because A and B are at same depth from top layer, and pressure at C, point C is nothing but atmospheric pressure plus rho G, and depth from top surface to point C is nothing but same again, H again. So rho GH. And now pressure at point D is nothing but atmospheric pressure plus rho G into depth. Point D is at same depth from top surface. So rho GH. So PA is equal to, now the conclusion is PA is equal to PB is equal to PC equal to PD. The pressures are same because they are at the same level. The pressure in a fluid at rest is the same at all points. Point A, point B, point C, point D is same at all points if they are at same level from the top surface, same depth from the top surface. Now I am going to explain the example number 1. Example number 1 is a boat. So here the example number 1 is the two thigh bones, each of the two thigh bones, each of the cross sectional area 10 centimeter square. Here cross sectional area A is equal to 10 centimeter square. I am converting area into SI system of unit. 1 centimeter square. 1 centimeter is nothing but 10 power minus 2 meters whole square. That is area A is equal to 10 into 10 power minus 4 meter square. Therefore, area A is equal to 10 into 10 power minus 4 meter square. Area in SI system of units. Total cross section area. This is area of one thigh bone, but here force is acting on two thigh bones. Total area is equal to area A equal to 2 into 10 into 10 to the power of minus 4 meter square. Okay, so that is area A is equal to 2 into 10 is nothing but 20 into 10 to the power of minus 4 meter square. Now support area is 10 centimeter square. Support the upper part of the human body is 40 kg. Upper part, that is above the thigh bones, the human mass is equal to 40 kg. So weight is acting on the thigh bone. the amount of force is nothing but weight acting on the thigh bone equal to m into g. So 40 into let g is equal to 10 meter per second square, that is 400 newtons. Now we got force also. Now estimate the average pressure sustained by the femurs. Pressure is nothing but force per unit area. Here the force is nothing but 400 newtons divided by area is 20 into 10 to the power of minus 4 meter square. By solving this, you will get 20 into 10 to the power of plus 4 Newton per meter square or Pascals. This is the answer. Now I am going to explain problem number 2 here. Example number 2. Here the example number 2 is what is the pressure on a swimmer 10 meters below the surface of the lake. Here depth h is equal to 10 meters and we know atmospheric pressure is equal to atmospheric pressure equal to 1.013 into 10 to the power of 5 pascals, and what is the pressure on a swimmer 10 meters below the surface of the lake. So absolute pressure on the swimmer 10 meters below the surface of the lake equal to, we know P is equal to PA plus rho GH. Here P is nothing but absolute pressure, PA is nothing but atmospheric pressure plus rho GH. Here absolute pressure at 10 meters below the surface of lake equal to absolute atmospheric pressure is nothing but 1.013 into 10 to the power of 5 pascals plus rho density. What is the fluid here? The fluid that is available in the lake is nothing but water. Water density is nothing but 1000 kg per meter cube into G is nothing but 9.8 or 9.8 meter per second square into H. H is how much? He has given H is equal to 10 meters. So here by calculating this, you will get 1.013 into 10 to the power of 5 pascals plus 1000 into 9.8, or we can consider it as 10. 1000 into 10 is nothing but 10,000. 10,000 into 10 is nothing but 1 lakh. By adding these two, you will get pressure P is equal to 1 lakh is nothing but 1 into 10 to the power of 5. 1 plus 1 is nothing but 2.013 into 10 to the power of 5 pascals is the answer for this question. Okay.